Alright, so today we're going to be learning about stoichiometry. We're going to have a quick introduction about what stoichiometry is. And then we're going to go into some word problems. We're going to do a balancing equation. We're going to talk about the mole concept, and we're going to be converting moles to grams and grams to moles. We're also going to be talking about ratios, significant digits, and we're also going to give you some suggestions for websites to look at if you need any extra help. And towards the end, we're going to be talking about limiting, reagent, and in excess, along with theoretical yield and percent yield. So what is stoichiometry? Very simple question. Let's answer it. So stoichiometry is the quantitative description of the proportions by moles of the substances in a chemical reaction. The stoichiometry of a reaction is the description of the relative quantities by moles of the reactants and products as they appear by the coefficients of a balanced equation. Quantitative information is only available through its stoichiometry. The work begins with the writing and balancing of an equation because this is the work that gives us the coefficients, the numbers that disclose the proportions by mole. Balanced equations are necessary to help chemists see the reaction's stoichiometry. So what that basically means is that stoichiometry has everything to do with the numbers and values and quantitative parts of chemical reactions. It's able to tell how much of a product there will be, how much they're supposed to, how much product you will get with a certain amount of reactants, and pretty much left, right, up, and down with that subject. And as you can see here, here's just an example or just a quick simple picture of stoichiometry that will help you understand a little bit more. So the amount of reactants before the reaction, and through stoichiometry we can figure what's the leftover reactant and the amounts of the products after. To help get a better understanding of stoichiometry, I've put together a little bit of an equation that we could apply to our real life. We have 2 pieces of bread plus 1 piece of cheese equaling a grilled cheese sandwich. Now this is very similar to any other chemical equation, except instead of chemicals we're just using everyday household food products. So through stoichiometry we can figure that if there is 10 pieces of bread and 4 pieces of cheese, we can figure through stoichiometry that you can only make a total of 4 grilled cheese sandwiches. That's because this right here, what we call the limiting reagent, which is what we'll get to later. That's a branch of stoichiometry that we'll learn about. Also in stoichiometry, we can figure that if there is 20 grams of bread, how many grams of cheese would we need to get 100 grams of grilled cheese? We'll be able to figure this out. We'll also be able to figure out how many grams of grilled cheese sandwich will we get with 20 grams of bread and 10 grams of cheese. These are all different things that we can figure in stoichiometry. But we'll explain how specifically to do that through the way. So here we're going to start off with balancing equations, which is a vital part of stoichiometry. It's the base layer of stoichiometry. Without it, there's really no else you can do in stoichiometry. So here you have a simple equation. You have CH4 plus O2 making CO2 plus H2O. Now, this chemical equation is looking good, it's looking nice, it's done, right? No, it's not. It is not a balanced chemical equation. Now, let's talk about that. What is an unbalanced chemical equation? Well, it's when a certain amount of molecules on one side is different than the other. Well, how does that work? Well, first off, let's count how many of each molecule is on each side of the equation. So, on the left side of the equation, let's put a line through the middle. On the left side, we have one carbon, right? That's it. So we got a 1. We have one carbon. And we also have 4 hydrogen. And over here we have a diatomic oxygen, so that's 2. On the right side of the equation, we have 1 carbon, we have 2, 3 oxygen, and we have 2 hydrogen. So, if we look at this equation, if somebody was to ask you, without you prior knowing what a balanced equation is, and knowing this information, would you say it is balanced? The average person would probably say no, and they're right. This is an unbalanced equation. The reason why is because of this. There is an uneven or unequal amount of molecules on both sides of the equation. In chemistry, both sides need to show the amount of molecules because you can't gain or lose molecules. You can't have 4 hydrogen and then all of a sudden have 2. You need to have 4. And same thing vice versa. So, let's try and balance it. Let's try and change these numbers and make them equal to each other. Let's try and have the same amount of hydrogen on one side as there is on the other. So, let's look back. So, let's look at this. Let's try and balance this. So let's start off with carbon. There's 1 on here and there's 1 over here. So let's just leave it. Those are equal to each other. There's 4 hydrogen over here and there's 2 over here. So how are we going to get 4 hydrogen? So simply enough, let's put a 2 to the left of it. 2 times 2 is 4. So now we have 4 hydrogen. But since this oxygen is attached, that means that there's 2 oxygen. So now there's 2 oxygen and 2 oxygen, so that's going to change this to 4 oxygen. Well, now our carbon and our hydrogen are equaled out. Now we have 4 oxygen and 2 oxygen over here. So how are we going to even this out? Let's go over back to the left side of the equation. How are we going to make 2 oxygen into 4 oxygen? Well, like before, let's just put a 2 to the left. Now, 2 times 2, that's 4. So now there's 4 oxygen. Now, let's take a look. We have equal amount of carbon, equal amount of hydrogen, and an equal amount of oxygen. Now, is our chemical equation balanced? Yes. Yes, it is. It is done. It is finished. It looks nice. It looks great. Put it on your refrigerator. It looks great. This is what a chemical equation looks like when it's balanced. You have the 2 to the left of the H2O and a 2 to the left of the O2. That is basically all that balancing equations is. So what exactly are moles? Well, the mole is a unit of measure used in chemistry to express amounts of a chemical substance. So the mole is not a physical, amount. It's more of like a representation or symbolic measurement. And here's a better understanding of what I mean by that. So as we can see here, in this chemical equation, O2 plus H2 making H2O, here's a very good representation of the mole. As you can see here, there's 2 molecules of hydrogen, but there's 2 moles of hydrogen molecules. Now, looking back at our balanced equation, remember the coefficients that we put next to the H2O in the H in the O2? Well, that's what these are here. Those numbers that we put in were actually representations of the amount of moles. We did it unknowingly. Whenever there is a chemical without a coefficient next to it, just put a 1 there. That means that there's just 1 mole. So, if we take a look here, there's 2 moles of hydrogen molecules, there's 1 mole of oxygen molecules, and there's 2 moles of water molecules. So, whatever amount there is of this hydrogen, it's going to be 2 times more than whatever the amount of the oxygen molecules are. And it's going to have exactly the same amount as the water molecules. Now, the thing that changes is that you can't say, well, if there's 50 grams of hydrogen, well, then that means there must be 25 grams of oxygen and there must be 50 grams of water. Well, no, that does not work. That does not work. You have to actually convert the moles or whatever. Let's say you get 25 grams. You're going to have to end up converting that to moles and then do all this math to figure out the actual exact amount. But these represent ratios, and that's what I wanted to show you. Here is a representation of the steps we're going to have to go through. So let's say I'm given 40 grams of oxygen and I want to figure out how many grams of another chemical it would take to make 2,500 grams of a product. These are the steps you would have to go through to find the amount of grams it would take. So I just wanted to show you this. And over time, throughout this video, you'll see that we're going to go through all of these steps. Now I'm going to show you how to convert moles to grams or grams to moles. And how to do that is to use this equation. Grams over grams per mole equals moles over 1. Now, let's say you have 40 grams of CH4. Excuse my terrible handwriting. Let's say you're given 40 grams of CH4. 40 grams is your given, so you can just put that in. 40 grams. Now the grams per mole is a measurement of the specific compound or chemical you're using. And it's different for whatever compound you're using. So let's take a look at what that is. So CH4 has carbon, hydrogen, and that's it. But it actually has 4 hydrogen. But anyways, let's take a look here. As you can see, carbon is right here, and it's 12.01. Well, in Miss Fontaine's class, we round that to the nearest whole number, so we're going to count that as 12. So carbon's 12, and over here, hydrogen is 1. Now, the grams per mole is pretty much those numbers added together. So there's 1 carbon. So we're just going to do 12 plus 1 times 4, because there's 4 hydrogen. So that's going to equal out to 16. It's as simple as that. So the grams per mole is going to be 16. Now we have enough information to figure out moles. That is what we're trying to figure out. So what we do here is just like any other math equation, we're just going to cross multiply. So 40 times 1 is 40, and then 16 times n. So you're going to have 16m equals 40 grams. Now let's figure that out. 40 divided by 16.
That is going to be 2.5. And that answer right there is your moles. So that is converting from 40 grams of CH4 to getting 2.5 moles of CH4. Now these both are representations of the amount of CH4, but one is in grams and one is in moles. They're two different representations, but they're both measurements. They are both measurements. So now, let's do this again. Let's convert from moles to grams. Let's go back. Let's use CH4 again. Let's say you're given 3.2 moles. Now you're given is in moles. So, just like we plugged in for grams last time, let's plug this in for moles. Let's plug it in. So let's get this out of the way. Let's put in 3.2 moles. Now, we know that the grams per mole is 16 already, because we already found it out before. So that's 16 grams per mole. Now, do we have enough information to find out grams? Yes, we do. Just like before, we're going to cross multiply to figure it out. So we're going to do 3.2 times 16, and that's going to equal 51.2, and that's going to be in grams. That is what you found. So now we went from 3.2 moles and we brought it to 51.2 grams. So 3.2 moles of CH4 equals 51.2 grams. Now, what we did right here applies to the relationships in chemical equations. And that's what I'll show you right now. Let's say we have the chemical equation like we did before. Now we're dealing with relationships now. We're getting into that type of stoichiometry. Now, this means that there is 1 mole CO2. Okay. So, when we look at these numbers 2 and 1 and 2 and 1, these are not the physical amounts of moles of each one. They're the ratios. For every 1 of CH4, there's going to be twice the amount, whatever that amount may be. And that's the same for so on. So technically, if you were to find how many moles there were, for instance, in this amount of CH4, that means you'd pretty much be able to figure out how many moles was in the rest. And the same thing with grams. If you were to figure out how many grams were in this amount of CH4, you could figure out how many moles or grams, for that matter, in any grouping, either in the products or in the reactants. So let's give an example. We're pretty much doing what we did before with the converting grams to moles and moles to grams, except let's apply it to an actual chemical equation. Let's apply it. So we're working with CH4 again. Let's say we find, okay, whenever you have an equation, let's do this. Whenever you do this, let's bring down the 1, bring down the 2, bring down the 1 and bring down the 2. You want to bring these down, separate them from the equations above, from the above. Let's put a little line above them. Okay, so let's say you are given 50 grams of CH4. Now some of you might be thinking, okay, if there's 50 grams of CH4, that means there must be 100 because the ratio is 2 to 1. Well, it is good thinking, but no, that's wrong. Because this 1 has to do with 1 of moles, and this is grams. You need to convert this to grams. So let's do that again. Let's do it again. Let's convert 50 grams to moles. So, like before, we're going to put the 50 here, 50 grams, because that's what we know. We're going to put 16, because that's the grams per mole, which we figured out through the through the periodic table. Again, all we need to do is just look at the numbers. Simple as that. And we need to find the moles. So that's what we're going to leave there. Well, we're going to do 16 times m, which is 16m. And we're going to have 50. So let's figure that. So that means that's going to be 16m is equal to 50. So let's do the math. We're going to have to divide 50 by 16. So let's do that. 50 by 16. That's going to mean that there's 3.125 moles. That is unclear right there. But that's our answer right there. Right there's our answer. So, if that's our answer, that means we can get all this work out of the way. 3.125. So, 3.125. So let's move it up here. We know that there's 3.125 there's 3.125 moles. So that means for every one, there's going to be 3.125. And it doesn't matter what type it is. These ratios are going to be the same. So now you can conclude that if there's 2 moles, if the ratio is 2 to 1, and 1 equals 3.215, then we could easily just figure that this is 6.250. And that this is 3.125. And that this is 6.250. It's as simple as that. Now, since you have all of those, this is in a perfect equation. But let's say that we want to figure out how many grams of H2O you would get. Let's figure out how many grams of H2O you'd get. Well, if it's 6.250 moles, we can easily figure out how many grams there is. You just gotta put H2O. So let's look back. Hydrogen is 1 each. So you don't include this. So that's going to be 2, and then oxygen in the periodic table is 16, I believe. But let's just double check. It keeps disappearing on me. Where are you going? Here it is. Alright, so here you can see that oxygen is 16. And hydrogen, which you can't see, is 1. So that means there's 2 H's and there's 1 oxygen. So that's going to be 2, 16, that's 18. So let's do the math again. It's as simple as this, guys. 18 times 6.250. It's going to be 112.5 grams. It's as easy as that. And that's how to find pretty much anything in an equation. You simplify, you balance the equations, then under it, for one of them, for whatever given there is, you convert the grams to moles, put it under, and then you compute that and conclude the moles for each and every one, and then do whatever is needed. Now that's how to do it in this way. Now we're going to take a look at significant digits. Significant figures or significant digits are critical when reporting scientific data because they give the reader an idea of how to tell, well, you could actually measure, report your data. Before looking at a few examples, let's summarize the rules for significant digits. All non-zero numbers, that is 1 through 9, are always significant. 2. All zeros between non-zero numbers are always significant. 3. All zeros which are simultaneously to the right of the decimal and at the end of a number are always significant. 4. All zeros which are to the left of a written decimal point are in a number more or equal to 10 are always significant. A helpful way to check rules 3 and 4 is to write a number in scientific notation. If you can / must get rid of the zeros, then they are not significant. Examples. How many significant figures are present in the following numbers? Well, let's take a look. 48,923. 1, 2, 3, 4, 5. There's 5 numbers that are all significant digits. So that's going to be 5. That's going to be a part of rule 1 because all numbers between 1 and 9 are significant automatically. Let's look at 3.967. Again, even though there's a decimal point, all of these are significant. All of them are significant. 1, 2, 3, because 4, 5, because that is 1 through 9. So that's going to be 4 significant digits. And then for 900.06, there's going to be 1, 2, 3, 4, 5 significant digits. And this is because all zeros between two numbers that are in rules 1, all zeros in between are significant, even if there is a decimal point in between or not. So that's 5 significant digits. Let's take a look at 0.00004. That's only 1 significant digit, because all zeros that come before a significant number are not significant. Now let's say it was 1.0004. That means that all of them would be significant. But this is not significant. Only 4 is. So there's only 1 significant digit in there. In Miss Fontaine's class, Q now. Now if we take a look at 8.1000, in Miss Fontaine's class, we say that all zeros after a number that is specified are significant. So 1, 2, 3, 4, 5. 8.100. All the zeros that come after are significant no matter what. All zeros that come before are not significant. So, there you have it. 501.040. That is 6 significant digits. 1, 2, 3, 4, 5, 6. Because let's take a look. There's 501. There's the 0 in between 5 and 1, so that means the 0 is significant along with these two. And then 104. The 1 and the 4 are significant, and since there's a 0 in between, that's also significant. And then we have a 0 that's after the 4, which also applies to the rules that we learned before. So that's also significant. So that makes this whole entire number full of 6 significant digits. Now if we take a look over here, 3 million, that has 1 significant digit. This is because even though there are zeros that come after the number, the zeros coming after a number only applies when it's after a decimal. So 3 million is actually only 1 significant digit. If it was 3.0000000, then it would be 7 significant digits. But since there's no decimal point in the middle, or that furthermore anywhere in there, there's only 1. If we take a look at 10.0, there's going to be 3 significant digits because the 0 here is significant and the 1 here is significant. So that means the 0 in between is significant. not to confuse you, let's clear this up for you. We do know that all zeros after the decimal are significant, no matter what, unless there is no number to the left side of the decimal. So let's say there was no 1 here. Let's say it was just blank. Let's say it was 0.01. Then everything to the left would be insignificant. But since there's a 1 here, that means that the 0 is significant after the decimal, the 1 is significant, and the 0 is significant. So that's a little bit on significant digits. Okay, now we're going to be talking about limiting reagent and in excess, or in A. Limiting reagent and in excess. So let's kind of step out of chemistry. Let's say you're trying to make a dozen cookies, and the recipe calls for 4 cups of flour and 1/4 cup of sugar. That together would make 12 perfectly good tasting cookies. But let's say for some reason you have 6 cups of sugar. 6 cups of flour. Let's say you have 6 cups of flour. Now, how many batches or how many cookies can you make with 6 cups of flour and 1/4 cup of sugar if you're trying to make perfectly good cookies? Well, it'd still only be 12 cookies. Because you're not going to use all 6 cups. You're only going to use 4 cups. You'd have 2 cups left over. Now, since there's going to be 2 cups left over because you're only going to be using 4, which is what the recipe calls for, that means the flour is in excess. And the sugar is going to be the limiting reagent. That is because the amount of cookies that can possibly be made is limited to the amount of sugar. The sugar limits the amount of cookies because there's less. If there was 6 cups of flour and 1/2 a cup of sugar, then that'd be a different story. You could probably still make more cookies. But that's not the case here. It is limiting the amount of cookies. And that's kind of like going back to our grilled cheese sandwich. If you have 10 pieces of bread and you only have 2 pieces of cheese, you can only make 2 grilled cheese sandwiches because there's only 2 pieces of cheese. It's very similar. They're both a limiting reagent. Now, let's try and apply this to actual chemistry. Let's try and apply this to chemistry. Let's try and apply this to chemistry. So, let's take that equation back in here. Let's don't save. Let's bring back this equation that we all know and love. The combustion of methane. Let's bring this back. Let's put in the coefficients 1 and 1. Let's bring down the coefficients like we did before. Let's say we were given 40 grams of CH4. 40 grams of CH4. We've already done that before, and it computes to just around 3.15 moles. Let's just say it was that. I don't know if that's right, but just for practical purposes, we're going to say it's 3.15 moles. From that, we can say that ideally there should be 6.30 moles of oxygen. And that's not always the case. That's not always the case. That is not always the case. So, let's say you're given, this is 40 grams. You're given 40 grams of CH4, and you're given 40 grams of oxygen. Okay? Now, this is the moles I should get. This is the moles I should get. But let's actually check. Let's actually check. This is how we can find our limiting reagent in this equation. So, we're going to put 40 grams over O2. So, that's going to be 16 plus 16 because there's 2, which is going to come out to 32 grams per mole, also known as the molar mass, equaling to moles over 1. Now, what this is going to do for us is actually compute the amount of moles we have. In an ideal equation, we should have 6.30 moles, but we only have 40 grams. We don't know if that's going to be if that's going to be less than what we need or more. So let's check. 40 times 1 is 40. So we're going to do 40 divided by 32 to get us 1.25 moles. Let's put this in a different color. 1.25 moles. 1.25 moles. Now let's take a look here. The ratio is 1 to 2. So if 3.15 is 1 and 2 is 6.30, and we actually found that we only have not 6.30 but 1.25, then this would be the limiting reagent because it is less than what is ideal. This is the ideal and it is less. Therefore, oxygen is the limiting reagent. And the methane is in excess. Because now, if there's 1.25 moles, and that's going to be 2, then the 1 would have to be half of whatever this is. So that would be just about 5, just about 5, 6, just about 0.65. Just about 0.65, just around there. For practical reasons, we're going to say it's 0.65. So, in actuality, we would need 0.65, but we have 3.15. So, that even shows more that CH4 is in excess. So that's showing how to find limiting agent and in excess. Okay, now we're going to be talking about theoretical yield and percent yield. And first off, I'd like to point out that in excess is actually spelled with an E. That's my dyslexia showing. But it's excess like that with an E. Anyways, once we go this far in a chemical equation, once we find our limiting reagent and our in excess, we can move on to the next step, which is finding our theoretical yield. So let's say with this amount of reactants that we have, we can figure how much of H2O we can get. And it's just as easy as doing what we've done before. Now, this is our actual... Here, let's clear some stuff up. That's 1.25. Okay. So, 1.25. Once we find that oxygen is the limiting reagent, we don't have to worry about CH4. We're done with him. We don't have to worry about him. You keep him in the equation, but we don't have to worry about him if we want to figure out the next few things. So we figured that we have 1.25 moles of oxygen, and that's when we have 40 grams. So, with that 40 grams, we want to figure how many grams or moles, depending on what's being asked, of H2O we can get. Well, we can do it right now. We can find out how many moles. Just put an X in here. That's what we're trying to figure out. 1.25 times 2, because we're cross multiplying. Think about it like going across like this. It's the same thing that we've done before. So we're going to do 1.25 times 2 equals 2.5. 2.5 equals 2x. So you're going to divide that by 2. And that's going to be 1.25, which is the same. It's the same number. It's the same ratio. So it's not surprising that it's 1.25. But I decided that we should go through that just in an example where we're trying to find a theoretical yield that does not have the same ratio. But we find that it's 1.25. But H2O is a whole different compound than that of oxygen. It's totally different. It has hydrogen, that's 2, and oxygen, so that's 18. It has a molar mass of 18, not 16, or not 32. So, we're going to figure out how many grams we would get. So we have 18 grams per mole. We have X amount of grams, because that's what we're trying to find, equaling, we know that there's 1.25 moles, and we know that there's one here. So we do 18 times 1.25 equaling 22.5, and that's what our X is. So we figured that we would make 22.5 grams of H2O with 40 grams of CH4 and 40 grams of 2O2. Of oxygen. 40 grams of oxygen. And that right there is our theoretical yield. Okay, so we just figured that 22.5 is our theoretical yield. And our theoretical yield is the amount that we suppose to get. It's the amount that we suppose to get. So if we know that we have 40 grams, and that 40 grams of O2 is equal to 1.25 moles, and then we could look at the ratio and say, okay, well, let's plug this in and see how many grams we should get. We figured that we should get 22.5 grams of H2O if we put in 40 grams of O2 and you put in 40 grams of methane. So that is your theoretical yield. Now we're going to be calculating percent yield, which is a lot like percent error. And that formula is going to be real... Excuse my terrible handwriting. It's very hard to do this on the computer. So real, which looks like roadie, but real over ideal. And real meaning the number that you get in the lab. So let's say our ideal number is 22.5. That's what we expect to get. But after doing the lab, we find that we only got 20 grams. So the real would be the 20 grams because that's what we actually got. And 22.5 would be the ideal because that's what we expected to get. So we're gonna plug that in. But it's gonna be times 100. So if we were to plug that in, let's just increase the size. It'd be 20 grams, which is real, and 22.5, which is ideal. So now we're going to divide 20 by 22.5, which comes out to be 88%. And that is a way of showing how close we were to getting the ideal. If we actually got 22.5, then our percent yield would be 100 because we got 100% of what we needed. We got a little bit less, so we got an 88%, which isn't too bad. So that is how to find percent yield and to find theoretical yield. Now, this can apply to anything. When you find the limiting reagent, that is when you're able to find the percent yield of any product. So if I wanted to find the percent yield of CO2, I could have done that too. I just have to do the same thing, except do 1 over x. Find the moles and then convert it to grams. And that's how you do it.
Throughout this video, we have done all of these steps. We were given the mass of CH4 and we converted it to moles using the molar mass. So throughout this whole video, we've actually done all of these steps, maybe without you knowing. We got the mass of CH4 and we converted it to moles by using the molar mass, which we learned how to get. Then we took the moles of the CH4, compared it with another, which we ended up comparing it with H2O, and we took the mole and we found the moles of the unknown, which was the H2O. Then we converted that moles to mass using the molar mass of H2O, and then we ended up finding the mass of the H2O, which was ended up being our theoretical yield. Also, throughout this video, we learned multiple formulas. We learned the grams. We learned the grams over grams per mole equaling moles over 1. We learned real over ideal times 100 for the percent yield. And we also learned basically through the steps in a problem how to do the rest. So, I'd say that it's safe to say that you have learned how to balance. I would say that you have learned how to balance. I would say that you've learned the mole concept. You've converted moles to grams and grams to moles. You've looked at ratios within chemical equations. You've learned about significant digits. You've done multiple practice problems with a solution. And also, we've learned about limiting reagent and an excess, along with theoretical yield and percent yield. So, I would now like to suggest to you some websites and a video that would help you on stoichiometry if this video did not help you. The first video is Stoichiometry by Khan Academy. They're a very, very well-known channel that have helped millions, literally millions of people with science and chemistry especially. As you can see, I mean, it has really great thumbs up. I highly suggest. I mean, if you look at some of these comments, this is so helpful. Thank you. This has taught me more than my school has taught me. I mean, come on, you have got to watch this video. Also, I want to bring you to the UC Davis Chemic Wiki. Chem Wiki. I looked at this. It has a lot of information, so I highly suggest you go to this website. As you can see here, it's URLs up here if you want to type it in. The third website I want to show you is on yzant.com. Just look at this. I'll put in the links in the description, but this is a really, really nice, well done page with many, many solutions and equations. So, highly suggest you do that. Again, I'd like to say thank you guys for watching this video, and I hope that helped.